So Vinogradov in 1937, so 3 points here. So in 1937, Vinogradov proved that a sufficiently large number, he didn't prove it. So Vinogradov, 1937, he proved that for sufficiently large is an integer and you can write n as the sum of 3 prime numbers. The reason I want to do this proof with you is that it is because it's a very famous and very great result, but also because it is an application of the things we did till now. At least one part of it is an application, for example, of the explicit formula and of the Siegel-Wells theorem and the zero field. So just to tell you that we do are linked to one another. They are not arbitrary things. Huh? Ah, yeah, yeah. So, yeah. So, odd number or sum of three prime numbers are not going to. Sorry, yeah. So, odd. Okay. So, so Newton did not prove that this is that the Goldbach conjecture. This is called the weak Goldbach. Okay, the weak Goldbach conjecture says that. It's now called the weak. So the weak Goldbach conjecture, also called the Ternary Goldbach conjecture. This says that every mod integer is sum of 2 times 3 can be less than the sum of 3 times. No, I mean less than 3. It is just a number. But more. Okay. It talks about the ternary group. And then you can do that. 3 P1 plus P2. Okay. There is also binary group. So let's talk about the ternary one. So what is Vinogradov proof is that for sufficiently large. So he did not qualify this sufficiently large. This was qualified. I mean, it was done much later. What is sufficiently large? Sufficiently means large. Large means large, but what is it? I mean, can we put a number on it? That was done later. And then this was so for so there is Vinogradov result. And on the other hand, we can verify using computer to a certain extent. And this can go quite high. I don't know exactly how much. I mean, now it's not so interesting anymore, but it was interesting. So So small values can be verified by hand. By hand means by computer. You can also do it by hand. I should mention about 20. So can be verified by hand. Yeah. Which means it can be verified not correctly. It can actually be, you can use some time. So what remains? Remains what we have rather done and what you can verify. There is a gap. There was a gap. So this gap was closed by closed recently in 2017. The gap between small and large and was closed by silver. Okay, so 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 all of a sudden you see we moved century, 1937. So none of us saw him, whereas we have all seen. Yeah, so he's a living man. So mathematics. So my aim is not to do this. Okay, neither to do this. But also, since we are at it, I want to tell you that there is the binary picture. And then this is not how Goldbach has stated it. It's the modern way of life. Yeah, do you know from which year the Goldbach conjecture is one of those. So binary Goldbach conjecture so good. It says that even every even integer is the sum of the stable integer greater than is the same as the sum of two. So this is open. Okay, open. I would like to talk a bit about this. And it should be clear to you that binary is if the binary conjecture is true, then the ternary conjecture is true. The binary Goldbach implies the ternary Goldbach. Clear? Why? Why does this like that? Yeah, but then you get and yeah, that's it. So that's obvious. Yeah. However, the other way is not true. Not that if the ternary is true, then the binary. So this all brings you to very very current mathematics that we are working on, and hasn't life hasn't stopped with the democracy. Okay. I mean, people outside, somehow I meet people outside analytics and theory, and they believe that the last thing that happened in our life was relevant. As if nothing has happened after. They don't know anything that has happened. If you are interested then you should know that things are going on, and not then. Things are going. Now, everything is not Vedogada and Landau and Adi and so on. However, if we don't know what they did, then we cannot do it. We have to learn what they did. Yeah. So that's the one which I'm going to. So I'll take the theorem as Noblara, and then there's something I want to tell you that this proof is there is for one part of the proof there is no cheating. We have done everything. So that part is fine. There is one part of the proof where there will be a little cheating in the sense that we have not done exponential sum. Okay. So the exponential sums is not studied. We have finite time as okay. So there are two things in this theorem. One is a major arc and a minor arc. Everything we do in the major arc we have to. Okay, I mean every tool that is used in the major arc, yes. Everything that we do in the minor arc we have not seen. Okay, so I will give you some references for completing it, and but I thought that you should have the book. So the whole term says that the theorem says that for any positive a greater than 0, you tell you the notation. So I'm going to use R of n to be the sum of n equal to K1 plus K2 plus K3. N is on. Okay. Here is the sum. And instead of writing this as 1, as we have seen as the standard technique, what would you like to write it as? What do we usually do? The difference between Chebyshev and the Random theorem. What we do usually smooth version. That? Yes? Louder, I don't see anything. That's lambda. Okay, the Mongo. I mean, this just makes calculation. So you can, like we saw yesterday, in 7 times 7 last time. So you can kind of cover the one. Yeah. So just the R of n. The question is whether R of n is greater than equal to 0 or. And then so Vinogradov not only said that for large n is possible, he actually gives a quantitative version of it. Yeah. Yeah, because, of course. Because if you have a network, you try that prior do that. If you have a prime, you can again break it down. Exactly. The prime also can be written. Okay. Yeah. You are more rigorous than I am. So for any n positive, we can have R of n, this R of n, okay, is equal to half of this. I will use f. For this, I will tell you what f of n, R of n, s of n square, okay, plus big O n square by log a. Okay, and so what is s of n? S of n is unit series, okay, this is equal to the product of prime divided n, 1 minus 1 upon 3 minus 1 square, and product of P that does not divide in 1 minus 1 by P minus 1. Yeah. Okay. So, she gives that very precise formulation. And so what happens? N is even, that's 0. Yeah. If you see a theorem, then first of all, we're not doing a proof or something. We should try to just look at it from far and see what it's trying to tell us. So supposing N is even, then S of N is 0. What is S of N? Here. This S of N is 0. Yeah. So R of N is going to be just comment. If N is even, then S of N is 0. We have all having N square to the power log 2n, and this is worse than the trivial bound. This is worse than the trivial bound. Yeah? What is the trivial bound? The trivial bound are of n log n to the power 4. Because here we have and so really quite. I mean, anyway, you don't. What happens when n is odd? Then S of n, this is almost 1. Yeah. If n is oh, there was almost a mistake. So if error is off, get remark. If n is off, then we see that S of n was 0, but now S of n is almost 1. Yeah. So R of n is greater than and if n is large. All right. In fact, to calculate this, yeah, it can be worked out. So you know that, you don't know, but I mean, this can be calculated. So if you choose the product, P, to get the case P equals 2, but you don't want P to be equal to 2. Yeah? If P is not equal to 2, then 1 minus 1 point, P minus 1 square is the, this is composed, you have 0.3, some other thing. Okay. And for the other one, for the product, 1 plus 1 upon P minus 4. Yeah. This is about 2.3 to 1. This is the numerical calculation of our problem. Which means that we will be somewhere between these 2 eventually, and therefore eventually means when n is large, the n square which will dominate. Okay. And give a bound for our because these are small. This needs to get actually means if you get 2 times, you get 1.32 here, 2.01 here. So, and if you add this to nothing, it's going to be very important. No, it's not that n is not inside. The n should not be not. No, it should. Wait, what's your question? Worse than the trivial. But the trivial, yeah. But this one is not. You have n squared like this. So and for source, and for source. Oh, yeah. So I think it's n log n to the power. Yeah. Yes. Yeah. So I will check this. It was an trivial bounds, but I will just check the definition of. So it is worth an trivial bounds, but I'll check this. So all right. So now let's see what we want to do. So the proof uses the circle method. I don't know, I probably have not seen the circle method here. So the circle method, to give you an idea of what it is about, the harding was circle method. This it should be also called the harding harding but I don't know. It's usually called harding. So what is this? So what we are going to do is so so we will consider a sum. Okay, this is exponential. Consider the sum. I mean, this one was in the other of alpha, and this is equal to sum of lambda n exponential 2 pi n alpha, and this is equal to summation lambda n, and this is equal to n exponential. I mean, this is the way of writing n. Okay, and we recover r of n. This is what graphs. So we have here 3 lines. Okay, K1, K2, and K3. Okay, we have 3 lines, K1, K2, K3. So So this F alpha has to be cubed. Okay. So F alpha has to be cubed. If you cube it, what happens? You get alpha cubed is equal to, when we write lambda k1, lambda k2, lambda k3, okay, potential 2 pi k1 plus k2 plus k3 and I, okay, where k1 plus k2 plus k3 should be less than or equal. So for convenience, we write this as r, little r and n and exponential and this way, right? Little r and n is equal to little r n is less than or equal to n. So now notice that as alpha cubed with the trigonometric polynomial, and you can write a Fourier series So we have this alpha cube is a trigonometric polynomial, and therefore I can put it up, okay, Fourier series R of n to be the integral of f alpha cube exponential minus alpha. And what about this integral? This integral, when is it large and when is it small? This depending on that we will make our two break. So supposing this alpha is close to a rational number, okay? If alpha is close to a rational number, the alpha is integral, okay? It's not by close to, I mean that I can make the difference small in terms of something like that, and sometimes people carry some custom results. Yeah. So and this one is close to a rational number with a small denominator. So if it's rational, there's a denominator, okay? Then the integral is large. This integral is large. And that's the idea. And it is small. It means the integral is small when alpha is far from 1. So this is the far from. So this is the dichotomy that we will use for array the Hardy-Littlewood circle method. Okay? So that's the Hardy-Littlewood circle method. Then we will use the Hardy-Littlewood circle method. So what we will do is, we will take all real numbers and quotient them by the integer r by then, and we will break them into some subdivisions. And these subdivisions, which will be these two possibilities. One part where we will be close to rational number, we'll call them the major part. I'll give you a definition. And otherwise, will be far from, one means far from other regular. Then it will be the complement, and we will call them the minor act. So for that, we will use the definition. We will say, if you have ever seen things, then you have seen things like that. Not necessarily the Hardy-Littlewood method, but just see if you have seen. Then you know that I take some function which is log b to the n, and q which is n upon log 2b to the power n. With b, the b will be chosen at the end of the proof in terms of the term that's not on the board, there was an a. Remember, every time I take an a, I get a result. Okay, so b, the b will be chosen at the end. Okay, you keep it moment b. Okay, and then the definition said p is this and q is that. Definition is for all q which is less than equal to 3, and for all a between 1 and q, with, as always, a and q be co-prime each other, we define then of a q, okay, this is equal to alpha, which is a real, not an integer, such that alpha between alpha minus a by q is Ternary 1 by. So that's what I said here. You say, I said alpha got close, so what is small denominator? So here we are quantifying this. So, okay, then if I see the union, I will go into subdivision. So every time we are having this for a and q, you create an equation, and then you take the union of all this n a q's. Then you get the the major arc. Okay? So it is all real numbers which are not integers, non-integers. Non-integers. They are real, but they are not integers. So that you can approximate it by a rational number. All real numbers are not rational. The distance, yeah, it is. So now you see the union of, so M is equal to the union of all such M AQ, AQ, okay, and this is the major arc, the major, okay. Now, in set of real numbers from which the integers have been removed, once you pull out capital F, there is a little f, okay. So that's the minus. The definition, the complement of n in z from which r from which has been removed um, is called the minor arc, and is denoted by little m. Okay. Okay. Maybe little m is not so useful. Little m. Is that this is the big one, this is the small one. Yeah? So usually use it little m. Okay. So first of all, this little m must not be empty. There must be some element in it. Yeah. So that means to take the union here, capital M, something should be left out still. Is that correct? That little m is not empty because I, in fact, theta disjoint. Yeah? So commit this model is not. Why is it not empty? It is not empty because if I take two different, so this is my definition, a by q. So suppose I have a by q, difference of a prime by a prime by q prime and n large. Okay. Then if I take A by q minus A prime by q prime. This is going to be greater than or equal to 1 upon q prime, which is greater than or equal to 1 by q square, which is greater than 2 by q, and therefore again is not the whole of R from which it has been. Now, I call this method the circle method. Have you any guess as to why we call it, why it's called the circle method? Can you guess from what how we have proceeded? Yeah? What is, when you remove R from this, then where are you? You are isomorphic to the unit circle. Therefore, this method is called the circle method. So that can be a comment. Okay. R with Z1 is isomorphic to the unit circle. So that's why we call it. This explains the name circle. So now we are going to study the major arc. And you will see all of the words that we used till now. Okay. So we have the first part is major. D. We are going to estimate so the size of the part. So let alpha be in one major arc. Q. And then we will take the Gauss sum. Remember the Gauss sum we talked about the very first week. Remember the Gauss sum? We studied it the very first. So tau of I. And we know that tau of so we are going to study the exponential. So you know that so that is denoted by tau of x, the phi of x, tau of phi bar. Okay, this is if I normalize by phi of q, then this is either 0 or n by 2, depending exponential n by 2, depending on whether n and 2 are beside each other or not. Okay. So that's an easy exercise. You can see this. Now you know about some now. And then we will take, remember that the major arc was defined using the distance from, the distance from some rational number. Yeah. So we have that a by q, aq, prime, and we given alpha be equal to a by q plus beta. So you don't want to get duplication, so you keep it as being open. Okay. And now you are going to study. What are you going to study? So yeah, you are going to study this. Remember, alpha at the alpha is equal to my one number, now that is exponential a by 2 exponential a beta. It will be a by 2 with beta, and for which k is less than or equal to 10 and L2 are in the following fact. And then you get some marathon. So, okay. So here, now we can use this, this property, and I can answer that here. So the one q dot is 1 by q summation lambda q summation 5 k e tau of k bar different side bar, okay, exponential k beta plus beta minus. So this is equal to 1 by 5 q sum of all which is in z, so z tau alpha sum of tau k lambda k exponential beta k of k greater than or equal to 10 plus error. Okay. So now you take this sum and use summation by part. And what does this mean? Take the, is there a problem? This proof follows very much the book of Goldbach, but some details are missing in the book. I mean, not missing, Goldbach is very. So sometimes the details are. So yes, X, which is in said by Q there, and is not zero. Yeah. Who is not there in the story? Q. So yeah, there's no X. So where is my X? No, it should be A. A. So now I'm going to take the inner part. Okay. So the inner part and line connection by part. What do you have? Yeah. Yeah. In fact, yeah. Yeah. Sorry. So taking the inner part now, that one, and applying what? Applying summation by part. So I take tau k, this one, tan k, lambda k, exponential beta. So tau k here, not lambda k, I k, and exponential beta k, okay, exponential beta k, of k, this is being less than 1. This gives me exponential n beta plus psi n psi. Number psi from the alphabetic and for 2I beta. Then I have an integral 1 to n potential u beta psi u chi dv. So this is going to be important. I mean, we are going to